Assalamualaikum and hi to our lecturer, Dr. Ibrahim Yaqub and Mr. Muhammad Afizal. So we are from group 17 going to present our experiment, which is dye dispersion. For introduction, the experiment of dye dispersion used the theory of entropy, which is a modern form of the second law of thermodynamics introduced by a German physicist named Rudolf Clausius. Entropy can be defined as a measure of the number of possible ways energy can be distributed in a system of molecules. During any spontaneous process, the total entropy change for a system and its surrounding is positive, and it can be mathematically written as delta S universe equals to the summation of delta S system and delta S surrounding that should be greater or equals to 0. In other words, the entropy of the universe is always increasing. So the example of entropy in daily life are ice melting process, sugar and salt dissolving, hot objects cooling down, etc. The figure shows the entropy creating disorder from the nicely organized particles to more disordered arrangement particles. The experiment of dye dispersion conducted in 3 different temperatures of water to determine the difference of the rate of dispersion of the dye. The experiment also enables the calculation of velocity of the dye in each of the temperatures. The velocity of dye obtained will further used to calculate the Reynolds number of the dye to confirm the pattern of the dye flow, where when R is less than 2000, it is laminar flow, and if R is greater than 2000 but less than 4000, it can be indicates that it is a critical flow. And lastly, when R is greater than 4000, it can be indicates that it is a turbulent flow.
The objectives of this experiment is to determine the relationship between the temperature of water and the rate of color dye dispersion. Secondly, to calculate the velocity of color dye dispersed in water and determine the Reynolds number.
So the variables in this experiment. First one, manifold variable, which is temperature of water. Second, dependent variable, which are rate of the dye dispersion, velocity of the dye, and Reynolds number. The third one, constant variable, size of glass and height of water. For materials and apparatus, we need to prepare 3 identical glasses, red dye, green dye and purple dye, hot water, room temperature water and cool water, syringe, thermometer and phone stopwatch. Methods in this experiment. The first step is 3 identical glasses were prepared and labeled as A, B and C. The second step, glass A, B and C was filled with cold water, water at room temperature and hot water respectively. All of the glasses were filled half full. The third step, temperature of water was measured using thermometer before 6 drops of red dye was placed in each glass. Fourth step, time taken for the red dye to reach the bottom of the glass and fully disperse was recorded using phone stopwatch. The fifth step, step 2 until 4 were repeated using green and purple dye. The last step is, all the observation and calculation were recorded in table 1.0. Experiment data for red dye. For glass A, which is in cool water, the temperature of water is 14.0 degrees Celsius. The height of water is 5 cm, and the time taken for the red dye to reach the bottom of the glass is 7.05 seconds. And lastly, time taken for the dye approximately fully dispersed in the water is 215.24 seconds. For glass B, which is in warm water, the temperature of water is 35 degrees Celsius. The height of water is 5 cm. Time taken for the red dye to reach the bottom of the glass is 4.25 seconds. Time taken for the dye approximately fully dispersed in the water is 139.97 seconds. For glass C, which is in hot water, the temperature of water is 69 degrees Celsius. Height of water is 5 cm. Time taken for the dye to reach the bottom of the glass is 2.06 seconds. And the time taken for the dye approximately fully dispersed in the water is 173 seconds.
My part is I will repeat the experiment using green dye at different temperature of water. Okay. For glass A, which is cold water, the temperature of water recorded is 5.0 degrees Celsius. Height of water is fixed for the three of the glasses, which is 5.0 cm, and time taken for the first drop to reach the bottom of the glass is at 3.10 seconds, and for the time taken for the green dye approximately fully dispersed is 500.55 seconds. Next, for glass B, which is warm water, the temperature of water recorded was 29.0 degrees Celsius, and height of water is 5.0 cm. Time taken for the first drop of green dye to reach the bottom of the glass is 2.64 seconds, and time taken for green dye approximately fully dispersed is 333.52 seconds. And lastly, for glass C, which is hot water, the temperature of water recorded was 83.0 degrees Celsius. Height of water measured is 5.0 cm, and time taken for the first drop of green dye to reach the bottom of the glass is 1.89. And lastly, time taken for green dye approximately fully dispersed is 120.22 seconds.
For my part, I use purple dye for the experiment. So first, for glass A, the temperature of cold water, is 12 degrees Celsius. Temperature for glass B, warm water, is 30 degrees Celsius. And for hot water, the temperature is 68 degrees Celsius. And the height of the water for each of the glass is constant, which is 5 cm. So the time taken for the first drop to reach the bottom of the glass for cold water takes 16.98 seconds, and for glass B it reduced to 12.92 seconds, and for hot water it reduced to 6.63 seconds. Next, for the time taken for the dye approximately fully dispersed for cold water, it takes 677.58 seconds. For glass B, warm water, it reduced to 328.96 seconds, and for hot water, it reduced to 85.56 seconds.
For my part, which is observations of dye dispersion for red dye. For glass A, which is in cool water, the first figure shows the true drop of red dye dispersion. The second figure, when the dye reached the bottom of the glass at 7.05 seconds. The third figure, when the dye approximately fully dispersed at 215.24 seconds. For glass B, which is water at room temperature. Okay. The first figure is the two drops of red dye dispersion, and the second figure is first dye that reached the bottom of the glass at 4.25 seconds, and the third figure is when the dye is approximately fully dispersed at 139.97 seconds. For glass C, which is in hot water, the first figure, 2 drops of red dye dispersion. For the second figure, when the dye reached the bottom of the glass at 2.06 seconds. The third figure, when the dye was approximately fully dispersed at 173 seconds.
Next, let's look at the observations on the dispersion of green dye at different temperature of the water. All of these pictures illustrate that green dye acts differently at different temperature of water, whether for which we can observe from the shape of the green dye at initial drop for glass A and glass B, also glass C. The observations at glass A using cold water. From all of these pictures, we can differentiate the condition of the green dye at three phase, which is the at initial, and secondly, the phase that the green dye have moved and dispersed to reach the bottom of the glass at 3.10 seconds, and lastly, at the final one, green dye have fully covered the water and approximately fully dispersed at 507 seconds. Next, let's look at the observations at glass B using warm water. Same as the previous one, we can see from these pictures that the green dye start to disperse once they have been dropped into the water, followed with the principle of entropy, especially we can see at the initial phase. Then, green dye more disperse and move to reach the bottom of the glass at 2.64 seconds until it reached the final phase where the green dye approximately fully dispersed and covered surface area of the water at time 333 seconds. Lastly, we can see the observations at glass C using hot water. It is obviously different from the observations at glass A and glass B. Especially you can see at the first picture where the green dye dispersed faster at initial time and already covered a big area once they have been dropped into the water. Then, green dye only required 1.89 seconds to reach the bottom of the glass until reach the final phase where the green dye approximately fully dispersed and covered the surface area of the water at time 120 seconds, which is the shortest among the others.
For my part, the observation of purple dye dispersion in glass A cold water. So the first figure shows the first 3 drops of purple dye dispersion. Second picture is when the dye reached the bottom of the glass at 16.98 seconds. And the last figure shows the dye approximately fully dispersed at 677.58 seconds. Next, observation of the purple dye dispersion in glass B, which is warm water. So the first figure shows the first 3 drops of purple dye dispersion, where the dye dispersed more compared to the dispersion in cold water. The second figure shows when dye reached the bottom of the glass at 12.92 seconds, and the last figure shows the dye approximately fully dispersed at 328.96 seconds. Overall, the dye dispersed more in room water compared to cold water. Lastly, the observation of purple dye dispersion in glass C hot water. So the first figure shows when the first 3 drops of purple dye dispersion. Second picture shows when the dye reached the bottom glass at 6.63 seconds, and the last picture shows when dye approximately fully dispersed at 85.56 seconds. So overall, the dispersion of the dye in hot water dispersed even more compared to the cold water and warm water.
We can make a brief discussion for this experiment. Based on the result obtained, It showed that the temperature is directly proportional to the rate of dye dispersion. This was because when the temperature increases, the kinetic energy of the particles has increased. The increased motion of the particles causes them to disperse faster. Therefore, at higher temperatures, the rate at which color dye particles will disperse is faster than at lower temperatures. It can be proven using this formula, which is the rate of dispersion equals to 1 divided by time taken for the color dye approximately fully dispersed. And next, for velocity of dye settling equals to height of water divided by the time taken for the color dye reach the bottom of the glass. However, there were some other factors that influenced the rate of color dye dispersion, which were the concentrations of color dye and surface area of water, as there will be collisions occur between particles and wall of the glass. In this experiment, the color dye also acts in a different type of fluid flows at various water temperature, as can be observed at the initial drop of dye, while also can be determined using the formula Reynolds number. Reynolds number equals to velocity of the drop settling times standard drop radius 0.2 mm divided by kinematic viscosity of water 1.307 mm squared per second. If the Reynolds number is less than 2000, the flow is called laminar flow. If the Reynolds number is more than 4000, the flow is called turbulent flow. And if the Reynolds number lies between 2000 and 4000, the flow may be laminar or turbulent, or in other words, transitional flow. In a conclusion, drops of color dye placed in hot water would disperse faster than drops of color dye placed in cold water because of the faster motion of particles in the fluid. Hence, the higher the temperature of water, the higher the rate of dispersion. Some safety precautions were taken in the experiment, such as handle the hot water carefully and keep the floor dry from any liquid where it may cause slippery and injuries. That's all from us. Thank you.